Hello, I am a graduate student in physics and I'll talk about a subject that is often overlooked into undergraduate lecture but which is really important to get a good grasp of Taylor series, Fourier series, and Fourier Transformation, which are tools that physicists often use. Since this is an advanced topic, you'll need to have learned about Taylor series, Fourier series, and Fourier Transformation. To make most of this lecture, you'll also need to have a good grasp of linear algebra. If you're not comfortable with any of these three subjects, I'll link video in the description that you should watch before watching this video. At the end of this video, I'll explain some quantum physics notion in the framework of function space. As an example, I'll explain the Heisenberg uncertainty principle. There's three interesting topics that will come across our video, but I won't have time to explain them thoroughly. If you're interested in any of them, you should read about them after this video. The first topic is the orthogonal polynomial, and by orthogonal polynomial, I mean any set of polynomial that is orthogonal. For example, one can think about the Bessel polynomial, the Hermite polynomial, or Laguerre, Legendre, and so on. There's a lot of them. The second topic is the weird distribution that is a delta Dirac. It is so strange that we can't call them a function. And finally, the third topic is the quantum measurement problem. To start this video, I'll ask a simple question. Are functions vectors? We remember from previous course that vector must satisfy two properties. First, we must be able to add two vectors together, and secondly, we need to be able to multiply a vector by a scalar. These two properties must not be too strange. For example, we need to have associativity and commutativity. Also, we need to have an identity element and a null element. As you might expect, functions respect all of these properties, so theoretically we could call a function a vector. When we think of vector, we might expect an arrow into space or some component. For example, here we have the vector v1, which has the component 1, 2, which represent an arrow into our plane. How does function relate to this? Because as we picture it, a function does not look like an arrow. To start to understand function as vector, we may approximate a function as the height of some rectangle. For example, here we have 10 rectangles which represent our function. The height of each rectangle corresponds to the coefficient, and our basis vector are each of these rectangles. If we upgrade our basis to 40 coefficient, we can see that we're already really close to our real function. If we would upgrade it even more, we will see that we'll get closer and closer to the real function. But first, let's think about what does the basis represent. For normal vector, we can think of basis as the direction x, y, and z. In our case, we have a basis that is composed of rectangles. We can push our analogy further by thinking about the space where the approximation of our function lives in. As we know, for normal vector, our space is the x, y, and z direction. For our approximation, our space is only the height of the first rectangle, the height of the second rectangle, the height of the third rectangle, and so on. Let's pause a moment and think about our function as an arrow into this new space. If we push the number of basis vector even higher, we'll get really close to the real function. For example, with 400 coefficient, our eyes think that we have the same as the real function. Mathematically, we know that this is not true and that we're still really far from the real function. To get the real function, what we'll need is not a finite number of rectangles, but an infinite number of rectangles. When we were approximating our function as a sum of rectangles, we were working into the discrete domain. Each of our basis vectors could be thought of as two Heaviside functions. The height of every Heaviside function was 1, and we were multiplying by a coefficient. When we switch from the discrete domain to the continuous domains, there's two things that happens. First, instead of representing our function as the summation of a coefficient times a basis vector, we represent our function as the integral of a coefficient times our basis vector. Secondly, we'll work with a rectangle that is not represented as an Heaviside function, but is instead represented as a delta Dirac. We need to use a delta Dirac because our rectangle must be infinitely thin, yet it must have an area under itself that is equal to 1. This is because we want our basis vector to be normalized. I have listed some properties of the delta Dirac, but I want to point out the last one, where we see that the integral of a delta Dirac times a function give us the value of the function at the point of the delta Dirac. Now that we've seen how to represent a function as a vector, I'll point out some of the classical operations that we do with a vector. First, we can see that the inner product of a function f and a function g is only given by the integral of f times g times a weight function. As we will see in the Fourier series and the Bessel series, the weight function can take many forms. As with vector, we can say that two functions are orthogonal if the inner product between both is equal to 0. We can also express a function as a linear combination of basis vector by doing the inner product of the function with this basis vector. Finally, we can define the square of the norm as the inner product of a function with itself. And now that we've seen how to represent a function as a linear combination of rectangles, which correspond to the position basis, we'll look at other bases that we can use to represent the function. The first basis we'll see is the Fourier basis, which corresponds to the momentum basis. Then we'll look at the Bessel basis, and finally at the Taylor basis. Using Fourier series, we see that we represent our function using a basis of cosinus and sinus function of different length. Our coefficient an and bn are found by doing the inner product of our basis vector with our function. We can also see that our weight function is 2 over the period of our cosinus or sinus. We say that the Fourier series corresponds to the momentum basis. This is because when we use Fourier series, we find the frequency of our function. The momentum is related to the frequency by the equation momentum equal the Planck constant h times the frequency. Finally, I've made you a graph to show you the first 4 cosinus and sinus basis vector. If we want, we can use fancier polynomial. For example, we can use the Fourier-Bessel polynomials, where each basis vector corresponds to a 0 of the Bessel function of order alpha. In the case of Bessel function, we'll get a stranger inner product because our weight function is x, and there's also a normalization constant because Bessel functions are not normalized. Even though our inner product is stranger, we can see that each coefficient is only obtained by doing the inner product of our basis vector with our function. And we can obtain our function by multiplying the coefficient by the basis vector and summing for every coefficient that we take into account. As before, I've made a graph showing the basis vector of our Bessel function for the Bessel function of order 0 and of order 1. You can see that for the Bessel function of order 0, we get a non-zero value at the origin. So, with the Bessel function of order 0, it is harder to modelize a function which has a value of 0 at the origin, so I would recommend to use a Bessel function of order 1 instead. Now let's take a look at Taylor series. As we can see, our Taylor series is really different from the Fourier and the Bessel series. We don't use a linear combination of coefficients. This is because the Taylor series is not orthogonal. For example, the basis vector 1 and x squared are not orthogonal between the interval -20 and 20. This is the equivalent of trying to represent a discrete vector using two basis vectors where the inner product of those two basis vectors is not 0. For completeness, I've made a graph showing the... For the next part of the video, I've made a graph of sinus of x and I'll show approximation of it using the position basis, the Fourier basis, the Taylor series, and the Bessel series. I'll change the number of coefficient, which is the n at the top left corner of the screen. I want you to take a particular look at the Fourier series where we see that our sinus function corresponds to the fifth coefficient of the Fourier basis. Now that we've seen the theory behind function space and its transformation, let's talk about quantum physics and the Heisenberg uncertainty principle. Any system can be represented as a wave function psi, where psi depends on numerous parameters, for example x, y, z, the time t, the spin s, and so on. We won't take into account all the parameters that the wave function depends on. We'll only look at one of them. For example, we can look at the x parameters. What we do is a projection into every basis vector that depends on x. We can now think of our system as a wave vector into the function space or as a function. Both are equivalent. The first strange thing that we'll see in quantum physics is that every possible state of a system is not a position into space, but one of the basis vector. For example, if we look at our wave vector, we can have two possible values, for example A and B, which correspond to orthogonal vector. For wave function, we can think of it as a delta Dirac, which already make a bit more sense. Now, let's say that we want to measure the position x of our system. What will happen? On one end, we know that our system can be any point into the function space, but we also know that only basis vector correspond to a value of the position. When we do a measurement, our system instantly collapses and our wave function becomes a basis vector. If our system is not one of the basis vector, we say that our system is in a superposition of state. So it is at the same time into different position x. The collapse of the wave function when we make a measure is called the quantum measurement problem, and is one of the main reasons why physicists say that quantum physics is really weird. Finally, the Heisenberg uncertainty principle states that we can't know the position and the momentum of a system at the same time. This is because when we do a measurement of the momentum, our system will collapse into one of the basis vector of the momentum, which is a sinusoidal wave. If we then try to measure the position of this sinusoidal wave, we'll get that our sinusoidal wave is made of an infinite sum of different basis vector of position, so we can get any value of position. On the other hand, if we first try to measure the position, we'll get one of the basis vector of position, which is a delta Dirac, and then when we'll try to measure the momentum of this delta Dirac, we'll get that our delta Dirac is made by an infinite sum of sinusoidal wave, which means that we can get any possible value of momentum. The best we can do to know the momentum and the position is to take an intermediate state between the position and the momentum basis. For example, if we take a wave function that is represented as a Gaussian into the position basis, we can then do its Fourier transform to find that it also looks like a Gaussian into the momentum basis. I don't want to do the full proof, but we can find out that Gaussian are a good intermediate state between the position and the momentum states, which means that the uncertainty on the position times the uncertainty into the momentum is equal to h bar over 2. Finally, the Heisenberg uncertainty principle states that the uncertainty on the position times the uncertainty into the momentum cannot go lower than h bar over 2. For a general state, it can go higher, but never lower. This completes my video. Finally, I'd like to thank Samuel Lemay, which helped me with the mathematics behind the scene, Grant Sanderson for inspiring me to make a video, and PacoVideoLectures, which made a brilliant video into function space, which my video is strongly inspired by.